So I want to continue our review of power series. Last time we saw what a power series was, that if a power series is obtained from an original function f, then we call it a Taylor series. We know that a Taylor series centered around x equals 0 is called a Maclaurin series. These are all things that you can review. And last time we worked out the Taylor series for e to the x around x equals 0. Now there are some special Taylor series that I'd like you to commit to memory, and the e to the x one is one of them. So let me just review that. So some special Taylor series around x equals 0. And the first one, as I said, is e to the x. So e to the x is 1 plus x squared over 2 factorial, or you can write 1 over 2 factorial times the x squared plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus forever. And of course I can write this using sigma notation if I like. I'm just as happy with this. N goes from 0 to infinity, x to the n over n factorial, with a reminder that 0 factorial equals 1. So this is a Taylor series I'd like you to commit to memory. And as I said last time, you can use this Taylor series to compute e to any power you want. If you want e squared, just plug in x equals 2 and take as many terms as is necessary to get whatever degree of accuracy you would like. Another one I'd like you to commit to memory is sine x. Sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. The next one will be minus, and so on forever. We go plus, minus, plus, minus, plus. We only have the odd exponents of x, and of course we have the odd factorials on the bottom. X over 1 factorial, which is just 1, 3 factorial, 5 factorial, 7 factorial, 9 factorial, and so on. So you can see that basically we have some of the terms that are in this original sequence. We have that one, and the x to the 5th, which is right there, which would be over here. And they alternate, instead of these, which are all positive, they alternate plus, minus, plus, minus. Again, these are 2 Taylor series that you learned in Calculus 2. And this, in particular, closed the circle on something that you started learning probably back in middle school, or whenever it was you were first exposed to the trigonometric functions. Up until this point, it would have been very difficult for you to compute just with pencil and paper, say something like sine of 20 degrees. But once you could have done it to a certain degree of accuracy if you remembered enough about the sine and cosine sum and difference formulas, but that's a very, very clunky way of doing it. Instead, what we do, of course, is change the 20 degrees into radians, because this only works if x is measured in radians. So we know how to change a number into radians. You take 20, and then you multiply by pi divided by 180, and you get a decimal value. And then you plug that into this expression, and now you can work sine of any angle you want out with pencil and paper. And that's something that you should want to be able to do. After all, your calculator can compute sine and cosine to a certain degree of accuracy of any angle you can type in. you should be able to also, that's something that you've been doing for a long time, using sines and cosines. So this gives us a nice convenient way of doing it. And cosine of x, here we have the odd terms. Cosine of x are the even ones, and again they alternate plus and minus. So cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus and plus minus plus minus the whole way down. There's an obvious resemblance between the sine and the cosine. Here we have the odd terms. Here we have the even terms. You can see what I mean by even. The powers are even. The factorials are even. But there's also an obvious resemblance between this and this. This is probably not the first time in your life that you've seen a resemblance between the trigonometric functions, the sinusoidal functions, and the exponential functions. Once you take a look, start looking at complex numbers, you see that the relationship between these is tighter than you thought. There's something called Euler's formula. If you remember Euler's formula, e to the I theta equals cos theta plus I sine theta. That's probably the first thing you ever saw that indicated that there was some sort of relationship between the sinusoidal functions and the exponential functions, even though their graphs don't look anything alike. The graphs of these, of course, oscillate, and the graph of this just grows exponentially. There's one more Taylor series I want you to commit to memory. Oh, one thing I should mention before I have the fourth one, this converges on negative infinity to infinity, and so does this, and so does this. So remember, we talked last time about where a power series can converge. These are all centered at x equals 0. And so it's possible, just by looking at this, that it converges just at x equals 0, or an interval centered at x equals 0 that's finite, or an infinite interval, in other words, negative infinity to infinity. And all three of these converge on negative infinity to infinity. So you can use these for any value of x you want from negative infinity to infinity. But there's one more Taylor series I want you to commit to memory, and that is 1 over 1 minus x. And the Taylor series for this, it's a very nice, simple looking Taylor series. It's 1 plus x squared plus x cubed plus x to the 4th plus and so on. All the coefficients are just 1, and they're all plus. And this only converges on the interval -1 to 1, the open interval -1 to 1, which is an interval centered at 0. All 4 of these Taylor series are centered at 0.